right, so we are looking at the Exam 2 review for Fall 2022 for linear algebra. First it says, state the formula for the inverse of a 2 by 2 matrix. Give an example of a non-zero 2 by 2 matrix that is not invertible. So the formula is A, B, C, D inverse is equal to 1 over AD minus BC and this was given in the book in Theorem 3.8. That was on page 165 of the textbook, if you're looking there. And then it needs an example of a non-zero matrix that's not invertible. So anything that has a zero determinant. So if it has a row or column of zeros, that'll work. Or anything where AD minus BC ends up adding to zero. So any example like that. I just gave a simple one. Consider that matrix. Find the inverse of A. So to find the inverse, I'm going to make a super augmented matrix with that and 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I'm going to row reduce that down. And so I can say row 3 equals row 3 minus row 1. And I can say row 2 is equal to, these numbers are kind of annoying. So I can do row 2 minus 3 halves row 1. So we're going to get fractions showing up here. So I have 2, 2, 1, 1, 0, 0. So row 1 remained unchanged. Row 2 is row 2 minus 3 halves row 1. So that's going to be 0 there. Here it's going to be negative 3 halves. And then I did 2 minus 3 halves times 2. So that will be 2 minus 3, so that'll be negative 1 there. And then 1 minus 3 halves would be negative 1 half. And so this would stay 1, and that would stay 0. Okay, row 3 is row 3 minus row 1. So that would give me 0. 1 minus 2 is negative 1. 2 minus 1 is 1. And then 0 minus 1 is negative 1. And then 0, 1, that'll stay the same. Okay, so I'm getting there a little bit at a time. So next I'm going to say row 3 is equal to row 3 minus row 2. So 2, 2, 1, 1, 0, 0, 0 minus 1 minus 1 half, minus 3 halves, 1, 0, and then I'll have 0, 0. Okay, so row 3 minus row 2. So 1 minus negative 1 half will be 3 halves, and then negative 1 minus negative 3 halves will be negative 1 plus 3 halves will be negative 1 half. And then 0 minus 1 will be negative 1, and then 1. Okay, we're getting there. So it just takes a while on these row reductions sometimes. Okay, so the last row is almost there. I'm going to multiply it by 2/3. So row 3 is equal to row 3 times 2/3. So that's going to give me 2, 2, 1, 1, 0, 0. 0. I'm going to do row 2 is negative row 2. Just get rid of that minus sign there. So I get 1, 1 half, 3 halves, negative 1, 0. And then I'll have row 3 is row 2/3 row 3. So 0, 0, 1. And then this gives me, okay, I'm multiplying it by 2/3. So that's going to give me 4/6. This gives me negative 1/3. And then negative 2/3. And then 2/3. Okay. And now we're getting close. We're going to get rid of that stuff in the above that bottom one. So we'll say row 2 is equal to row 2 minus 1/2 row 3, and row 1 is equal to row 1 minus row 3. And so 2, 2, 0, 0, 1, 0, 0, 0, 1, but we've got to figure out what happened over here. Okay, so row 1 is row 1 minus row 3. So 1 minus 1/3 would be 2/3. And 0 minus 2/3 is 2/3. 0 minus negative 2/3 is just positive 2/3. 0 minus 2/3 is negative 2/3. Okay, on the middle row, we have row 2 is row 2 minus 1/2 row 3. So row 2, so 3/2 minus 1/6. So that gives me 4/3. And then if I do negative 1 minus 1/3, that gives me negative 4/3. And then when I do 0 minus 1/3, that gives me negative 1/3. Okay, almost there. So then I could do row 1 divided by 2. So I get 1, 1, 0, 1/3, 1/3, negative 1/3, and 0, 1, 0, 4/3, negative 4/3, negative 1/3, and then 0, 0, 1, negative 1/3, negative 2/3, 2/3. Okay, and I've got one last step to go. I have row 1 equals row 1 minus row 2, and so that gives me 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, I'm almost there. And then I'll have, okay, row 1 is row 1 minus row 2. So 1/3 minus 4/3. So that'll be negative 3/3, so negative 1. And then 1/3 plus 4/3 will be 5/3. And then negative 1/3 plus 1/3 is 0. So that is my inverse matrix. So then it says use A inverse to find the solution to the matrix equation AX equals B. So I can solve this by saying X equals A inverse B. So A inverse I found 1, 5/3, negative 1, 5/3, 0, 4/3, negative 4/3, negative 1/3, negative 1/3, negative 2/3, 2/3. And I want to multiply that by the vector 2, 1, 0. And so when I get that, that gives me my answer. So I have negative 2 plus 5/3. So that gives me negative 1/3. And then 8/3 minus 4/3 gives me 4/3. And then if I do negative 2/3 minus 2/3 gives me negative 4/3. So that is my solution to AX equals B. Okay. This one we worked out in class, so I'll kind of talk through it. So we can find x1, which is p times x naught, which is 0.5 0.3, 0.5, 0.7 times x naught, which is 0.5, 0.5. So after one iteration, we end up with 0.4, 0.6. X2 is equal to p squared x naught, or I could think of it as p times x1. So I'm going to do it that way because I think it's a little easier. 0.5, 0.3, 0.5, 0.7 times 0.4, 0.6, and that gives me 0.38 and 0.62. So there are my x1 and x2. Then it says find a steady state probability vector for the Markov chain. And so what I have here is 0.5, 0.3, 0.5, 0.7 times x1, x2 equals x1, x2. And so I can think of this as subtracting off 1 times the lambda. So I can find this by subtracting that away. So I have 0.5 minus 1, so negative 0.5, 0.3, 0.5, and then 0.7 minus 1 is negative 0.3, 0, 0, and I want to solve for that null space. So if I do that, I'm going to multiply by, so I can see that that bottom row is going to cancel, and then the top row I'm going to multiply by negative 10 to get 5, 3, 0, 0, 0, 0. And so this is my pivot here, and this is my free variable. So I'm going to say x2 equals t, x1 is equal to negative 3/5 t. Now that doesn't add to 1, so I need to figure out what t needs to be to make that work. So negative 3/5 t plus t needs to equal 1. So that is 8/5. So let's see. Whoops, I made an error. This should be a negative 3. When I multiply by negative 10, I get that negative 3 there. So this will be positive 3/5 t. Okay, I was wondering why I got something different. Yeah. So then that gives me 8/5 t equals 1. So t is equal to 5/8. So then I get x1 is equal to 3/5 times 5/8, which is 3/8. And x2 is equal to 5/8. So that's my steady state vector. The next one is this matrix diagonalizable. So the first thing I can do is I can look and I can see my eigenvectors. So I get lambda equals 1 with multiplicity 2, and then I have lambda equals 2. So if I had distinct eigenvalues, the answer is immediately yes. But I don't have indistinct eigenvectors. So what I need to do is I need to make sure whether or not we will get in linearly independent eigenvectors. Okay, so let's compute it. So if I plug in 1, I have 1 minus 1, 1, 0. And then I'll have 0, 1 minus 1, 1, and then 0, 0, 2 minus 1, which equals 0, 1, 1, 0, 1, 0, 1, 0, 0, 1. Which goes to 0, 1, 0, 0, 0, 1, 0, 0, 0. So I can see my pivots are here and here, which means this is my free variable. So I'm going to say x1 equals t, x2 is equal to 0, and x3 is also equal to 0 because I have x2 here equals 0. So those are my, so the eigenspace related to 1 is equal to the span of the vector 1, 0, 0. And I could actually stop here because I know that that multiplicity 2 eigenvector only had, or eigenvalue only had one eigenvector, so that means that it is not diagonalizable because I'm only going to get one eigenvector out of that one because it only had multiplicity 1. So I know it's not diagonalizable. So this will only give me one eigenvalue vector. It will only give me one eigenvector. Okay, find the eigenvalues of that, and for each eigenvalue, find a basis for its eigenspace. Okay, so I can see the eigenvalues actually right there on the diagonal. So 3, 1, 1. So let's go ahead and write them down. So 3 minus, so 3 minus 3 is 0. 1 minus 3 is negative 2. 1 minus 0 is negative 2. Or 1 minus 3 is negative 2. Okay, so I can do row 3 is equal to row 3 minus 2 row 2. So I get 0, 4, so that's going to be me 8. So these are my leading ones. So this is my free variable. So let's let t equal, x3 equal t. So I have 5x1 minus 2x2 equals 0. And then I have x2 minus 2t equals 0. So x2 is equal to 2t. And then I can plug that in up here, and I get 5x1 minus 2 times 2t, so minus 4t equals 0. So I can add that over. I get x1 is equal to 4/5 t. And so my eigenspace related to 3 is a one-dimensional eigenspace. It's the span of 4/5. X2 was 2t, and then x3 was t. Okay, so that's the eigen. So we can see here that, so 3 gives us is a multiplicity 1, it gives us one eigenvector. Okay, let's look at for lambda equal 1. So I get 3 minus 1 is 2, 0, 0. And then I have 5, 1 minus 1 is 0. And then 10, 4, 0. Okay, and so I can go ahead and clear out the 5 and the 10. So and then I'll get 0, 1, 0, 0. So after I reduce that, I'm going to get that. The 5 and 10 are going to clear out from this 2. It's not going to mess with anything else because I have zeros here. And then the 4 I could divide by 4 and I get a 1. Okay, so there are my 2 pivots here and here. So there's my free variable. So it's a one-dimensional eigenspace. So E1 is going to be, so x3 is equal to t. X2 is going to be equal to 0, and x1 also will be equal to 0. So my eigenspace related to 1 will be the span of 0, 0, 1. Okay, and so I end up with this eigenspace that is two-dimensional. I only have 2 linearly independent eigenvectors, so this actually is not diagonalizable either. All right, so for this one, we want to find the matrix of that linear transformation. And so we're going to be using a theorem from the textbook that says that to find the matrix of that linear transformation, we just really need to figure out what happens to our standard basis vectors. So T of 1, 0 and T of 0, 1. So we can draw a picture and kind of think about what's going to happen. So what happens to 1, 0? Well, it's rotated by 45 degrees, so it goes here. That is to root 2 over 2, root 2 over 2, and then it reflects. So it ends up here at negative root 2 over 2, root 2 over 2. And so that is the image of 1, 0. And the image of 0, 1, well, it starts out here, and then it rotates by 45 degrees, and then reflects over here. So it ends up at root 2 over 2, root 2 over 2. Okay, and so then to write the matrix down, the theorem says I just take the first column is T of E1, and the second column is T of E2. And so for however many dimensions we have, we'll have that many vectors. So it's negative root 2 over 2, root 2 over 2, and root 2 over 2, root 2 over 2. Okay. This is let A and B be 3 by 3 matrices, and suppose that determinant of A is negative 5, determinant of B is 3. So the relevant theorems are going to refer to theorems about determinants. I'm supposed to compute the determinant of 2A inverse B. So note that I have a scalar multiple, and then I have an inverse, and then I have a product. So we can have this determinant of a product is determinant of the product of the determinants, which is nice. Determinant of A inverse actually ends up being 1 over the determinant of A. And the determinant of Ka is equal to k to the n times the determinant of A. So the determinant of 2A inverse B is equal to 2 cubed determinant of A inverse B, which is equal to 2 cubed times the determinant of A inverse times the determinant of B, that's by this product one, and then that is 2 to the third times 1 over determinant of A times determinant of B. So this gives me 2 cubed times 1 over negative 5 times 3. Last page, true or false? Okay, this one is false because the matrix, we did this in class. The matrix A is 1, 1, 1, 0, minus 1, 0, 0, 0, minus 1, has only 2 eigenvalues, but 3 eigenvectors. So it is diagonalizable. Okay, so if it has unique eigenvalues, then it's definitely diagonalizable. If it doesn't have n unique eigenvalues, then you have to do a little bit more investigating to figure out if it has n unique eigenvectors. Okay, this one, if A is similar to B, then A and B have the same eigenspaces. So the theorem that we have says that they have the same eigenvalues. They're going to have the same eigenvalues, but not necessarily the same eigenspaces. For all square matrices A, we have determinant of negative A equals determinant of A. So we're going to use this theorem that determinant of Ka is equal to k to the n times the determinant of A. So the determinant of negative 1A is going to equal -1 to the n times the determinant of a. So depending on what n is, that could be true, but if n is odd, it is false. So it's not true in general, so we're going to say it's false. If the next one, if a is invertible, then 0 is not an eigenvalue. This comes straight from the fundamental theorem of invertible matrices. So this is true. This is from the fundamental theorem of invertible matrices, and that is on theorem 4.17 on page 296. Then if T from R to R is a linear transformation such that that's true, then this is true. Okay, so we need to go back to the definition of linear transformation. So if you look back in section 3.6, there is a definition of linear transformation. And one of the things it says is that T of C times V is equal to C times T of B. So we're going to see if that applies here. So T of 3, -6 is equal to T of -3 times -1, 2. So I can relate it back to the what I know. I know that this is true, right? So I can say that that is, since it's a linear transformation, that -3 can pull out. And then I can compute what is T of 1, 2. Well, I know it's 1, 7. And then if I multiply that constant, I get -3, -21, which is what I was hoping to get. And so since I know that this is true and I know that it's a linear transformation, I can conclude that this is true.